Okay, everybody, so welcome back. Um, and no, homework has not been assigned already. I'll post your first homework assignment either later today or tomorrow. Um, so you can be looking for it, and it'll be due next week. Okay, what do we have? We ended yesterday with discussion of like the general form that this fitting um, uh, some data points to a line, the least squares line, looks like. So it looks like this. I'm not going to restate the general theorems for the more general curve fittings that we're about to do, but you're going to see the form that they take, and you're going to see exactly like what is actually going on here. Um, so this was our statement of what the least squares line is. So it is the line that we obtain by obtaining the least square solution to this system or this matrix equation here. That least square solution gives us slope and y-intercept that gives us the least squares line, right? And so the example that we used yesterday was this one. Obviously, in practice, you're going to have many more data points than this, but this is just to show you how this is going. Okay, so now, as my lead-in, kind of the thing that I talked about before we had ever written any of this stuff down, which is what if you have data points that just looking at them, right, a line is just completely unsuitable for, right? So say you have data points that maybe look something like this, right? They look like this. And so you look at that thing and you say, well, okay, a line is maybe not a great fit for these because I'm going to have some of these vertical distances be way too big. But like something that does this maybe is better, right? So a parabola, something that looks like this is a better fit for this data. The question is, can I do that? Now, you might immediately say, oh, there's all kinds of curves that I can use. Uh, but before we go too crazy, we're going to do some of the simple examples, and then we're going to talk about what we can't use this to do. Um, so we can't exactly use it to curve fit or to fit like any type of curve um, to these data points, but we can use it somewhat, and we can use it in slightly more general situations. So um, here's the idea. We can fit a curve. Okay. So long as the function in question. So first of all, it's going to be the graph of function. As long as the function in question depends linearly uh, on the unknown variables. So what do I mean by this? So the function in question needs to look like this. Where each of these f sub i's are functions of x, but the unknown variables that we seek are actually these a sub i's. Okay, so the f sub i's are known, and the a sub i's are unknown. Okay, so whenever you have a quantity, you want to be, I want to be careful here not to confuse you when I say that something is linear here. So the things that what the linear has to do with is the dependence on these a sub i's. But the f sub i's may not be linear functions. That's kind of the point here. Okay. So let's do an example. So let's say that we have data points. Let's say our data points. Again, in practice, you would have hundreds or thousands of data points, not just 4, but this is so that I don't have to plot thousands of points by hand. Say our data points -1, 2, 0, 0, 1, 2, and 2, 3. Okay. Let's see what these actually look like. So what do these look like if I plot these? So one of them is the origin, 0, 0. And let me make some indications here of scale. So we have -1, 2 is another one of these points. We have 1, 2 is one of these points. And 2, 3. So you see, were it not for this point, maybe you would just say a line is best here, but because of this point, you say, well, okay. And I mean, maybe the thing is, and we're going to talk about this later, there's no answer here, right? Like, so when you have data points, like asking for a curve that best fits them, sometimes even if it might look like a parabola would do a better job, maybe the line actually does a better job. These are mostly on a line, and then this thing is just one outlier. Sometimes that's a better fit than some parabola that maybe doesn't fit it as well. And of course there is a direct way we can check this. You might think about how we can check which is a better fit. Right? Hint, it's checking the least squares error, right? So checking the least squares error is actually the quantity that tells you that the thing is the best fit by comparing them. Or maybe not the best fit, but a better fit than some other model. So that's the thing. When you choose a curve here that you think is a good fit for the data or fits the data well, that's a choice that you've made that might not be the right one. Okay, there may be a curve that fits it better, right? So this is just part of this process here. And so let's say that we think a parabola is what is going on here. Is how we're going to obtain a curve that fits this data well. So if that is what we are going to do, then going back to our points here, what we are going to seek, right? So we seek a function f of x, which is ax squared plus bx plus c. Now notice this is in fact of this form that I'm required here. This is a f1 plus b f2 plus c times a constant function, if you like, which you could call f3. It's just times the constant function 1 here. This is the function x squared, and this is the identity function x. Okay. So this does in fact fit this thing. So when you look at this, it's important that when we talk about this, you look at this function and say, oh, this depends linearly on the unknown parameters a, b, and c. Right? Don't get confused that this is an x squared here, okay? Because this is what we mean, that it is in this form. Okay. All right. So, what now? Well, let's do the same thing that we did for a line when we had this situation, right? So this is what we seek. So ideally, right, like we would find a parabola such that all of these points lie on it, right? But what would it mean for all of these points to lie on the parabola? Well, it would mean, just looking at this here, so for the first point to lie on the parabola, what would that mean? It means that a times minus 1 squared plus b times minus 1 plus c times 1, if you like, right, is equal to 2, the y value for that point. So this is the equation that would be satisfied if the point minus 1, 2 lied on this parabola. If the point 0, 0 lied on this parabola, the equation that would be satisfied is a times 0 squared plus b times 0 plus c times 1. Notice we're not plugging in anything here. Don't get confused, right? This is just the form that this is in. Okay, and that is equal to 0. Okay. If the point 1, 2 is on the parabola, the equation that would be satisfied is a times 1 squared plus b times 1 plus c times 1 is equal to 2. And then lastly, if the point 2, 3 is on the parabola, the equation that would be satisfied is a times 2 squared plus b times 2 plus c times 1, and that would be equal to 3. These 4 equations would be satisfied simultaneously if all 4 of the points simultaneously lied on the same parabola. Now, just as in the previous case where we had a least squares line, right, that we were attempting to solve for, here we have naturally a matrix equation that arises out of this. So what does it look like? Maybe I'll write it on the next page. No, I'll write it here and then I'll continue on the next page. So what does this look like? This, I have a matrix here, minus 1 squared. So this would be 1, minus 1, 1. The next would be 0, 0, 1. The next would be 1 squared is 1, 1, 1. And lastly, 2 squared is 4, 2, 1, times the vector containing the unknown parameters a, b, and c. These are the coefficients of the polynomial. And that is equal to the vector containing the y values here, 2, 0, 2, 3. Okay. All right. So here is my matrix equation that, if it had a solution, would indicate that all 4 of these points lie on the same parabola. Now, looking at these, they don't look like they actually lie on the same parabola here. Right? I know my scale's a little questionable here, maybe, so this doesn't maybe look as good as it could. But these don't really lie on the same parabola, so what am I going to do? Well, I do the thing that I always do with least squares. The whole point is I have a matrix equation. It doesn't have a solution, and I want to find as close of a solution as I can, right? This is my least square solution. So I write out the normal equations here. So what are the normal equations? Right, so if this is my, just to keep refreshing memory, right? If this is A and this is X and this is B, my normal equations are A transpose A times X is equal to A transpose B. Now, when we're writing the normal equations and solving for the solution that we get at the end, we usually write it as x hat. We know that the solution is going to be an x hat, but if you leave it as x bar, like it doesn't matter, right? It's the whole point is the solution to this. Once you found the solution, you can relabel it as x hat, whatever, however you want to do that. Rewriting this then, so this would be 1 minus 1 1 0 0 1 1 1 1 4 2 1 transpose times the matrix itself times this vector ABC. I'm putting a hat over it to indicate the solution that I get. It's going to be the least square solution. This is 1 minus 1 1 0 0 1 1 1 1 4 2 1 transpose times that vector, that right hand side vector 2 0 2 3. Okay. Okay, this is a 4 by 3 matrix, so it's transposed as a 3 by 4 matrix. So 3 by 4 times 4 by 3, I should get a 3 by 3 here. The 3 by 3 I get after multiplying these two out is the following. This is 18, 8, 6, 8, 6, 2, 6, 2, 4. Okay. This solution vector I seek is still the same, right? It's still unknown. This is equal to, here I should get a 3 by 1, so that is a column vector with 3 entries. And what I get here is a 16, 6, 7. And I multiply those out. Okay. Now I can solve at this point. I'm in the case where this thing is invertible, I believe. So inverting this, I get that my solution is 0.75 minus 0.25 0.75, which means what? I've gotten my least square solution in this context, which means what? This means that the parabola that has these as its parameters a, b, and c is the best fit, right? So i.e., the parabola, which is f of x, is 0.75 x squared minus 0.25 times x plus 0.75 is the best fit for the data. Now, when we say best fit, right, what do we mean? We have to be careful. We do not mean that like we have just declared this to be the best fit among all possible curves, right? What we mean is that this is the best fit for parabolas. So if you're choosing a parabola to do this, this is the one that does it the best. Okay, it doesn't mean that it's better at doing it than some line might be. It doesn't mean that it's better than doing it at some cubic or than some cubic. It means that it's the best fit if we're talking just about parabolas. Okay. All right. So then going back to our data, like what does this actually look like if I were to sketch this in? It looks, something like this maybe. Right? Maybe you find that to be good, right? But remember, what is it that's being done? What's being done is these vertical distances, the sums of their squares are being minimized still. So whether we're talking about a line, a parabola, or any other type of like polynomial curve here, what is being done is the sum of the squares of these vertical distances, right? These differences between, we'll say, observed y value and predicted y value are the sum of the squares of those differences, those distances, are being minimized. Okay. Easy to remember that when you remember the name, right? Least squares. Okay. So this is what I've got. Now, here is the question. Moving on to another example. Say now I have data points minus 1, 1, 1, 3, 2, 10. Okay. And now I plot these. I'm not even going to plot them here, but I plot these and I notice, hey, you know, it looks kind of like these follow the following curve, right? So say I think that these follow a curve of the form f of x is ax plus sine of bx. Okay. Now, you might immediately say, wait, what if I had the b outside here? Is that okay? We're going to see the difference here, right? Why this is bad, right? So note, if we think that these 3 points, you know, like if we do the thing where we say, okay, ideally all 3 of these points would lie on the same function that looks like this. So if that is what is going on here, there should be 3 equations satisfied here. So the first one for minus 1, 1 would be a times minus 1 plus sine of b times minus 1. Okay, and that would be equal to the y value here, which is 1. And then for 1, 3, I would have a times 1 plus the sine of b, and that'd be equal to 3. And then for the last one, I would have a times 2 plus the sine of 10b, and that would be equal, this would be 2b, sorry, not 10. And this would be equal to 10. Okay. But then what's the problem with this system of equations? Well, it's that this function did not depend linearly on the unknowns. The unknowns here are a and b, right? And b appears in the argument of sine here, so I can't write this as a matrix equation, right? Can't rewrite as a matrix equation. Because the unknown parameter b is in the argument for sine, I can't peel it out, right? So that's what I mean here. And so we can't do that sort of thing. But if you notice, like, hey, what if, you know, I thought that it looked like ax plus b sine x? Is that okay? And the answer is yes, that's fine. Now, typically, right, you have polynomial things. This is like your first attempt because they are simpler to deal with, and and cover. There's a lot of reasons why with polynomials alone you can do a lot of things. In fact, you might know that of course it's not always the best way of thinking about it, but sine itself is a power series. Right, and so truncating that power series at your favorite degree, right? You could think of an approximation by polynomials to sine if you wanted to. So anyway, polynomials are very frequently used here rather than introducing things like sine, cosine, and other things. But there's absolutely nothing wrong with this. So if instead we had said, hey, we think our function is best fit, or sorry, our data is best fit by a thing that looks like this. This is fine, right? This is fine. This is not. Okay. All right, so that's just giving you an idea. Yeah, okay, great. So somebody even said it in chat. What if we do Taylor series expansion of sine? Of course, yes, you can do this. And not just for sine, any function the Taylor series expansion of, you could approximate by polynomials. You could absolutely do that, but it's even better than that because we don't need to restrict ourselves that much. We can actually just do it with full sine. In fact, we're going to do that in a later example. Just show you that we're not 100% restricted to polynomials here. We can actually do much more general curve fitting. But what we are restricted by is the fact that these parameters, the function that we seek, must depend linearly on those parameters. That's the important bit. Okay. So before I do some more examples, I'm going to go ahead and say that actually we don't have to stop here, right? So in fact, we can increase the dimension. What do I mean by that? We can do, instead of curve fitting, we can do surface fitting. Or, if you have a problem, surface you tend to think of as a two-dimensional thing. I'm going to do an example of that, but there's not even a reason to restrict ourselves in that way. We could think of this as, surface or hypersurface fitting, or fitting this in a way that, suppose we have data points that are, k tuples, right? So say that we have data points that, instead of being ordered pairs, are ordered k tuples. Okay, which of course is just a fancy way of saying they look like this. Now, why k instead of n? Well, it's because I used n for another thing that you're about to see, right? I used n for the number of functions we had for the predicted function. So that's why I'm using k here. So these are ordered k tuples now. So let's say that our data points look like this. Obviously, there's a lot of reasons why sometimes your data points would be k tuples instead of just ordered pairs, right? So this is maybe you're tracking several quantities at once, several quantities corresponding to some value. So for some x value, you have a y and z value that are determined in some other way. These are different quantities that depend on the x value, maybe, or vice versa. You have a z value that depends on the x and y value. So that's the idea. Okay, so let's say that this is the situation that I'm in. Then the function that I seek, right? I seek ideally some function that perfectly fits the data. And again, the only requirement I have really is that it linearly depends on the unknown quantity. So here, first unknown is a1, and then I have a function of k variables f sub 1 plus a sub 2 times my second function of k variables f sub 2, and so on, all the way to f sub n, a sub n times f sub n. This is my last function of k variables. So this is the thing that I seek. Okay. And so ultimately, the same process is going to take place here. Like, the only thing is that the computations are more tedious, but of course for doing this with computer aid, these are not significantly less tedious. Not really. And so let's do an example of exactly this thing. So consider the data points 1, 1, 6, 3, 1, 22, 5, 4, 95, and -2, 0, 10. Okay. Now, the big step here is figuring out what surface I think these 3 points are best fit by, or what they seem to be following. Right? It might be hard to do that just like looking at some 2D representation of graphing these things in 3D. But we'll say I have help, so it's not just me; it's a bunch of other people also doing it, and we're all using computers to help us see what it is that this thing fits. And I come up with the idea that, hey, maybe this thing fits an elliptic paraboloid, right? So what about an elliptic paraboloid? Now at this step, right, on one hand, you might say, well, like, what if you're wrong? But in a way, once you've fixed the curve or the shape that you are trying to fit the data to, or trying to fit to the data rather, once you fix that, you can't really be wrong unless you make an error in the actual least squares computation. And what that means is that once you decide on what the shape of the thing looks like, finding the least squares solution, even if it's a really bad fit, that still it is the best fit for that thing. So the error is not in the computation you did. The error was in choosing the shape to begin with. Once you've chosen the shape, right, even if it ends up not being a great fit compared to some other things you could have chosen, you can't really be wrong in that sense, right? It's okay. You tried to fit to a bunch of points that were almost on a line. You tried to fit them, or you tried to fit an exponential function instead. You guessed an exponential function was the best fit, and it's just not, and it's terrible compared to the line. You can still find the best fitting exponential function, right? Even if it's not objectively, in some sense, a good fit. Okay. So, what about an elliptic paraboloid? Elliptic paraboloid is of the form f of xy is equal to ax squared plus by squared plus c. Okay, and so again, this is our usual thing. We say ideally, right, we would love it if when we went to check, all 4 of these points simultaneously lied on the same elliptic paraboloid. But what would the system of equations look like for that? So for the first point, this would be a times 1 squared plus b times 1 squared plus c times 1, because it's always times 1 here, is equal to 6. Okay, and then next, a times 3 squared, this is for the second point, plus b times 1 squared plus c times 1 is equal to 22. And then a times 5 squared plus b times 4 squared plus c times 1 is equal to 95. And then lastly, for this last point, a times minus 2 squared plus b times 0 squared plus c times 1 is equal to 10. And all four of these equations would be satisfied simultaneously. Okay. That's how this would go. Now, rewriting this as a matrix equation, of course, what do I have here? This would be 1, 1, 1. Next would be 9, 1, 1. Next would be 25, 16, 1. And next would be 4, 0, 1. Times the coefficients a, b, and c. That is equal to the right-hand side vector that contains these y values, so 6, or z values in this case, 22, 95, 10. Okay, so this is my matrix equation. So again, this is my ax equals b. I want to write out my normal equations. So my normal equations, A transpose A times x hat is equal to A transpose B. What does that look like? This is 1, 1, 1, 9, 1, 1, 25, 16, 1, 4, 0, 1 transpose times the matrix itself. Times this unknown vector. We were still using A, B, and C here. Times A transpose, or is equal to A transpose times the vector B. Which is 6, 22, 95, 10. All right, so there's my normal equations. If I multiply this out with the aid of computer, what do I get? I get, this is 723. I'm reading row-wise here, 410, 39, 410, 258, 18, 39, 18, 4, times A, B, C hat, and that is equal to the vector 2,619, 1,548, and 133. So that if I invert this thing and solve, I get my least square solution. ABC is approximately 2.0048, 2.7083, and lastly 1.5155. Okay. And so what this means is that the elliptic paraboloid which was my original, here, just bringing it back, this thing, right? What is the best fit? It is the elliptic paraboloid 2.0048x squared plus 2.7083y squared plus 1.5155 is my best fit. Again, best fit here among the elliptic paraboloids, right? This doesn't mean that there's not some surface that fits it better than this ultimately does. Okay. There's a couple things that I want to notice that you may have noticed in all of these examples we did. In this example, because the numbers are the way they are, you might have really noticed it, right? But what can you say about this matrix? Someone, if you notice it in the chat, you can let me know. But what can you say about that matrix right there? What kind of matrix is that? Is the question I'm asking. There's something special about that matrix. And the question is, what is it? So what is it that is special about that matrix? You'll notice that this same property was had by the previous matrices at this point in the normal equations. When you multiply out A transpose A, you get this matrix, and it has this property in all of the examples we've done so far. So what is it? Okay, well, notice that this matrix is 410, 39, 18. This matrix is a matrix that if you transpose it, it doesn't change it, right? We call a matrix like that symmetric. So notice that I could transpose this matrix and it's the same thing. This matrix is symmetric. What is a symmetric matrix? A symmetric matrix is a matrix that when you transpose it, it's equal to itself. Now, why did I use M here instead of A? Because I've used A up here, so it would be confusing. But let's just check, right? So we have the matrix M, which is A transpose A. Okay. What if we transpose this thing, right? So what if I do M transpose? Well, M transpose is A transpose A transpose, but the transpose reverses the order, so this would be A transpose times A transpose transpose, and the transpose of the transpose is the matrix itself, so this would be A transpose A, which is M. So this matrix A transpose A is symmetric. Okay, now you could say, how does that help? Symmetric matrices with real entries. These are very, very nice. There's a lot of very, very nice properties about them. We'll talk about that later when it comes up. But this is just something to take note of. That symmetric matrices tend to be very, very nice ones. Okay. All right. So this is an example of doing curve fitting where we're not even curve fitting anymore. We are now like surface fitting. But you see how it's exactly the same. It is in the same spirit for sure, right? This definitely belongs to the family of curve fitting. Okay. So now, getting back to this question, which is what this means in practice. So as I've said previously, the goal here, right, is to ultimately make predictions based on data that is necessarily limited, right? Since data is inherently limited, it's a finite list of data points, and the data is just the data, right? Data is just the thing you have collected. There is no reason that it has to fit very well with any shape that you dream up necessarily, right? This is what I mean when I say there's not a like right answer here typically, right? You'd have to be very lucky to collect 1,000 data points and have every single point lie on some curve that you can find, right? And even if it did, even if you were in that situation, the point ultimately is to use this model, right? So choosing a function is really choosing a model. Because ultimately, like you are not doing this just for fun. You are not playing connect the dots just for fun. You're doing this so that ultimately you can make predictions based on this data, and those predictions are going to use the values of the function, right, that you don't have data points for. That's the idea. The idea is you can't possibly collect all the data. You can only collect a finite amount. But the curve contains infinitely many points, and ideally, if that curve matches the trend of the data enough, you can use the points of the curve that you don't have data for to predict, right, the values of the data that you haven't collected yet. That's the point of doing this, and that's why choosing a function is really choosing your model, right? So even if you had a model, or even if you had data points that fit perfectly some curve, and you say, okay, I'm choosing this curve as my function. Well, now what do you have to do? When you make a prediction, you then need to verify that the prediction is actually or actually worked, right, or came true, which involves collecting another data point, and that data point either matches or it doesn't, right? And there's no reason to say that it has to, right? Maybe you have a curve that perfectly fits the 3 data points you've collected, and then you make a prediction at a 4th value, and that 4th value is just totally off, right? Even if those 3 points were collinear, right? They all lied on a line. You use that same line. The 4th point is just not, right, on that line. So that could always happen, no matter how many data points or no matter how good the fit is. You could have a data point that just simply doesn't match. But anyway, in practice, that's how this would go. You would have points, you would have data points, you would choose your model, choose your function, you'd make prediction, then you would recalibrate, you would collect more data to see whether or not you need to alter the model or whether you are happy continuing on using this model to make predictions. So that's how this goes. Okay. So, but the thing to not lose sight of is that, the data is just data. It doesn't necessarily fit your model or a nice, tidy model that you want to dream up. It doesn't necessarily fit those things. So, here's an example. Okay. You'd say, okay, suppose I have health insurance cost data. In the form TD as ordered pairs, where T is time. This will be years after the year 2000. And D is the average yearly cost taken over all individuals. Now, the actual data set here would be massive, right? So you would have a ridiculous number of data here if you actually had access to all this stuff. But for the purpose of this example, I'm just going to take a few points. So let's say the points in question are 0, 2, 2, 5, 10, 30, 1375, and 15, 150. Okay. And you might notice, right, that when you start plotting this, one thing that you're running into is that there's a scale issue between the axes here. So the T and D axes are not scaling exactly at the same rate because the D seems to be growing like much faster than the T. Okay, and so when you go to plot this, right, the picture you would get would be something like this. So we would have like a point here for the 0, 2, and then we'd have like another point like here, or the 2, 5, and then we have a point like here, and then here, and then here, right? Something like that. So maybe you look at that and you say, well, that looks like maybe that is fit by a parabola. Or maybe you look at it and say, it kind of looks like something that is fit by an exponential. So those are your guesses, right? So your guesses. Try either a parabola or an exponential. So these are our two options. Now, here again, maybe if you hadn't listened to my rants about how data is just data and you don't there's not a like right answer here. You might be confused for a second and say, well, how do I know which one is the right one? The answer is, well, both of them might be garbage at actually predicting this, but the point is which one is the better of the two, right? So, in like an objective sense, maybe both of them don't do a good job, but you can at least say which one does a better job, okay, than the other. So that's something that you can say. So let's do the exponential first, just because we've already done parabola. So let's do something a little bit different first. So what is our guess? Our guess for the exponential thing, we guess that our function of t looks like this. It's like a plus b e to the t here. Now notice that going back, remember the thing that we couldn't do, right? This b needed to be outside the sign. It can't be inside the argument for sign, so that there's a linear dependence on the unknowns here. So here we followed that, right? This b is not in the exponent here. It is outside of it. Okay, but you might notice that we're going to be plugging in a 15 here, and e to the 15 is huge. It's like a really big number, okay? And it is this is already, I'm looking at this and I'm saying, well, I don't think this is going to be a good job, or this is going to do a good job, just because e to the 15 is like absolutely massive, okay? And so the thing about exponential functions is that they all have this shape relatively, right? Like we're not nailing down like the scale here. Like we looked at the shape overall and picked an exponential function. And exponential functions, regardless of what their base is, look like that. Right? That's what exponential functions look like. So there's no reason we have to pick e. We pick e, by default because in some ways it's the best one because of properties of its derivative and things like that. But here, that's not really relevant. We're looking for a thing that has the best shape here, and this e to the t is just going to be too big. So let's pick a different base other than e. Okay. So what do I want? Like I want this b to the 15 to like approximately be 150. That's the point. This is my these two are like my problem points because they're the second value is outscaling the third one massively. So I want b to the 15 to be like 150. So I want b to approximately be like the 15th root of 150. But the 15th root of 150 is like 1.39. So that's like 1.4. So let's try 1.4 as our base instead of e. Okay, if 1.4 is our base instead of e, then for this last term, this b to the 15 is approximately going to be 150. So this is going to work much better. So the new guess, here we'll cross that one out. My new guess in the exponential case is that this is like a plus b times 1.4 to the t. This is my guess. Okay. So then we have 5 data points, so we are going to get 5 equations here. Okay, so let's see what those equations look like. Here's my data points. Here's my exponential guess. And so now I'm going to write out the 5 equations that I would get if all 5 of these points lied exactly on this thing. So what would those look like? I would have f of 0 would be a plus b times 1.4 to the 0. And that needs to equal my y value. The point was 0, 2, so this would be 2, right? So just one more time, flashing these points on screen for you so that we're going to get these 5 equations so that you're not confused as to where these numbers come from. F of 2 then is going to be a plus b times 1.4 squared, and that will equal 5 because the point is 2, 5. Okay, f of 10 is going to be a plus b times 1.4 to the 10, and that is equal to 30. And then f of 13 is a plus b times 1.4 to the 13, and that is equal to 75. And then lastly, f of 15 is a plus b times 1.4 to the 15th, and that is equal to 150. These 5 equations, we'd like them to be satisfied simultaneously. They're not going to have a solution, so then we find least square solution. So what would the corresponding matrix equation look like? So these a's, of course, are all multiplying 1. The way that we've written this. So this would then be the following. So this would be 1, 1.4 to the 0, 1, 1.4 squared, 1, 1.4 to the 10, 1, 1.4 to the 13, and then lastly 1 and 1.4 to the 15. This is times the vector AB. Right, and this is equal to my vector of those d values here. So this would be 2, 5, 30, 75, 150. Okay. Okay. So this is my x equals b. Do our normal thing. I'm not going to write it all out here. We know what to do by now. So write out my normal equations, blah, blah, blah. What do I get? The solution, the least square solution here is 1.8982 and 0.9463. So then this function, f of t, is 1.8982 plus 0.9463 times 1.4 to the t. This would be our best fit among exponential functions of that form. Okay. Now, how do I know how good of a fit this is? So you might, again, you might say, wait, isn't it the best fit? Well, again, it's the best fitting exponential thing of that form. But my question is more like, how good is it overall? Now, overall compared against everything, I can't do that comparison all at once. But I can pairwise compare it against another model. I'm going to go ahead and compute the thing that I have to compute in order to do that, so that when the other model comes along, we have that in front of us. But the answer to this question, if this is a question, the answer is compute its least squares error. So this is what I do. What is the least squares error here? Remember, the least squares error is this thing. It is the length of the vector ax hat minus b. So that is the length of here. A is 1, 1.40, 1, 1.4 squared, 1, 1.4 to the 10th, 1, 1.4 to the 13th, and lastly 1, 1.4 to the 15th. That's our A, times this vector we found, it's our least square solution, minus the vector B. Remember, this is telling you how close this thing is to being a solution, right? That is what this is telling you. Okay, and we know that this minimizes among the same type of object here, this exponential thing, this minimizes this error. So what is this error? This is 2.7601. Okay. So this is the least squares error when our choice for model is this exponential thing. So now, let's try the quadratic guess. So in this case, I'm guessing that my function looks like this. We'll say at squared plus bt plus c. If that is the case, mimicking the same thing, again, just to remind you what the points are, here's the points. In our example, there they are. Okay, what does this look like? If all 5 of those points lied on this parabola, this quadratic thing, then the equations that would result would be f of 0, which is a times 0 squared plus b times 0 plus c. F of 2 would be, and this would be 2 in this case because the point is 0, 2. Next point is 2, 5, so this would be a times 2 squared plus b times 2 plus c is equal to 5. F of 10 is a times 10 squared plus b times 10 plus c is equal to 30. And then f of 13 would be a times 13 squared plus b times 13 plus c is equal to 75. And then lastly, f of 15 is a times 15 squared plus b times 15 plus c is equal to 150. And then when I write out the actual matrix equation that I have here, what would I get? I would get 0, 0, 1. This is my left-hand side here. Here I get 4, 2, 1. And then 100, 10, 1. And then I would get 169, 13, 1. And then I would get 225, 15, 1. Times the vector ABC is equal to my right-hand side containing these values on the right here in these equations. So 2, 5, 30, 75, 150. Okay. Find the least square solutions, or solution. The least square solution is what? It is, writing this out exactly, this is 1.3577. Next is minus 11.7172. And next is 10.9079. Here we go. There it is. This gives me a quadratic function f that is 1.3577 t squared minus 11.7172 times t plus 10.9079. This is my quadratic best fit. Now again, in order to compute how good of a fit this is, or how good of a model this is, I want to compute its least squares error. Right? So, least squares error is ax hat minus b, or the length of that vector, which is the length of the following. So rewriting this matrix is 0, 0, 1, 4, 2, 1, 110, 1, 169, 13, 1, 225, 15, 1. Times this vector that I found, this least square solution, which is 1.3577 minus 11.7172, and then 10.9079 minus a vector on the right, which is 2, 5, 30, 75, 150. And when you compute this length, you will find that it is like 21.9904. But remember, what was our least squares error for the exponential thing? Oh, 2.7601. So this is definitely greater than 2.7601. Therefore, the exponential fit is better. So, again, to stress, this does not mean that the exponential fit is best among all possible curves I could fit it to. It just means that compared to the quadratic fit that we tried, the exponential fit is better. So you can't find the best fit like globally all at the same time, but you can absolutely compare them pairwise. You can compare the things and see which is the better fit for the data that you have, right? Now again, right, this data, even if this fit was even better, even if this was almost zero, doesn't really mean that the data is exponential, right? For all you know, the next data point you collect totally throws that off. The next 10 data points you collect might really throw that off, right? But the point is, for the data you have, this is telling you relatively which is the better fit. Okay? So that's the main thing I would stress. The exponential here does a better job than the quadratic, but you can't say it does like the best job or anything like that, no matter how small this thing is, right? Unless the thing is literally zero, in which case your least square solution is just the solution. In which case, there's no reason to find a closest solution. You just have a solution. So that's the deal. Now, as I have mentioned many times by now, the point. Once we are satisfied with our least squares function, We can use it to make predictions. Okay, which is a key thing that we want to do. So for instance, in the health insurance example, what if I wanted to predict healthcare costs in 2020? Well, we're in 2026, so predicting healthcare costs in 2020, you know, you don't have to call me a genius for being able to do that. If I wanted to predict healthcare costs in 2020, so I collected this data prior to 2020, I wanted to predict healthcare costs in 2020. If I used quadratic, if I use the quadratic model here, then what would I do? I would simply evaluate this function at 20. Notice that in the data points I had, right, I had only collected data up to 2015, right? So this is me predicting 5 years out here, simply by plugging in 20 here. So this would be 1.3577 times 20 squared minus 11.7172 times 20 plus 10.9079, and this is approximately 319.6439. Okay. So this would be my predicted based on that. So here, you know, this would be in another 5 years, my value, according to this quadratic model, would be 319 instead of 150. So quite the growth in 5 years. All right. And then say that in another way, I wanted to know when the healthcare costs might hit a certain value, right? Say I want to know when costs might hit, say, 400. How would I do that? I just solve for f of t is equal to 400. It's another way that I might predict this. So if I do this for the case of the quadratic, maybe I get negative solutions. I'm not interested in the negative time in this context, so I would just toss out the negative solution. So I'm only going to have a single solution here, single positive solution. And if you only pay attention to the positive solutions, what you get is that t is approximately 21.7851. So when, at what time past the year 2000 will the cost hit 400? According to this quadratic model, it would be like 21.7851 years. Okay, after the year 2000. So like 2020 in mid 2022, right? Or sorry, in like mid 2021. But yeah. So anyway, this is like these are two like very basic examples of how you might make predictions. You could ask more complicated sorts of questions, but ultimately, right, this is kind of the goal. The goal is to obtain a model that's as good as possible, fits the data as good as it possibly can, and then make predictions based on that. Of course, you would revisit those predictions, see how close you got once you have more data. Maybe revise the model, or maybe not if your model did a great job, right? So that's ultimately the idea with all of this stuff. And so that is pretty much all I want to say about curve fitting. We have other uses for least squares, as we'll see. But curve fitting is certainly like the most immediate one and the thing that comes up most frequently. So here's like a pretty self-contained treatment of it. The homework that I post, I'll probably post homework tomorrow, and it'll be due either Monday or Tuesday at 11:59. So I'll let you know. You can look for the Elms announcement for that. It will mostly concern this stuff. It might have like a one topic. It might have like a little bit of what I talk about tomorrow, but it's mostly going to concern least squares, curve fitting, maybe some general linear algebra review type stuff. So anyway, that is the deal. So I will see you all during lecture tomorrow. And like I said, have a look for my Elms announcement. You're probably going to get it after lecture tomorrow, so maybe don't worry about it tonight. But after lecture tomorrow, you can look for my homework announcement. But yeah, I will see you all tomorrow.